Great to be back and meet everybody face to face. It's been so long, it feels a long, long time. And it's also very good to see so many material suppliers here today, because as trace dimensions get finer and finer, sometimes your customers, the PCB fabricators, start to question the measurements of decay that you so carefully make. And I'm going to show you a simple correction you can make to measurements that will make your measured decay align much better with the tested decay in the fabrication industry. What's a controlled impedance trace on a PCB? It's really a simulation of a coaxial cable. And I think you can all agree, if you buy a coax cable from a supplier, 50 ohms or 75 ohms or 100 ohms, but it's always that set value. So a question to ask is, if it's a metre long, is it still 50 ohms? And if it's 2 metres long, or 1 millimetre long, is it still 50 ohms? 10 millimetres? 50 centimetres? Or if I took this 50 ohm cable and cut it in half, would that make two 25 ohm cables? Because that's the kind of trap that some fabricators are falling into. And during the process of this, I'll reveal what's happening. So they're different lengths, but the same cable impedance is true for all of them. So we're simulating a coaxial cable within a PCB by designing it in a specific way. This illusion that fabricators are getting that the impedance changes with length, it's really only crept into place as geometries have got finer and finer. What can happen there is that the DC resistance has clouded your measurement. I was a bit worried earlier this morning when Alan mentioned me and Emma having a dance, because I can't dance, Emma is very skilled at dancing. It did remind me of a question one of my colleagues asked Dr. Eric Bogatin. He said that, Dr. Bogatin, which is right, simulation or measurement? Expecting to hear the answer, it's the measurement. And Dr. Bogatin said, I'm sorry, they're both wrong, to the horror of my colleague, complete horror. But what he said is, simulation tells you what you ought to get, measurement tells you what you actually get, but the measurement may be subject to errors too, and you need to think what the right answer is and look at the measurement and look at the simulation, and both things may need adjusting. With broader geometries, measurement of impedance has been pretty straightforward. There's nothing been clouding the measurement, but as the geometries have got finer and finer, we're starting to see DC resistance clouding your measurement, specifically in fine line designs. It's new to us in the PCB industry, but if you go back to the 50s and 60s, cable manufacturers have known about this for a long, long time, and series loss in a cable is just another spec. How many ohms per metre, per kilometre, series resistance is there in a cable? But the geometries we worked with in PCBs, I mean, we can quite safely ignore that until now. This is a copy of a page in a book, which was a Tektronix TDR book written in 1967, which shows the effect of DC resistance in cables. In fact, it even proposes using the slope of the TDR trace to calculate how many ohms per metre you're losing. This is a 50 ohm line, and this is a 50 ohm line, but there's a series resistance line in the middle. And it means that the trace rises here and then flattens out here, but this line and this line are both identical, one sitting on the other end of a series resistance. So it makes the impedance on the measurement appear to rise with length, and the trap the fabricator's falling into is believing that the impedance meter is always correct, but when you get fine lines, you've got to remove that DC resistance from the measurement. Signal integrity engineers would use a flashy word, they call that de-embedding. We need to de-embed the series resistance from the measurement so we get the correct characteristic impedance of the PCB trace. And if you don't remove the series resistance from the impedance measurement, that's the wrong inference that could take place, that the data sheet's wrong. You know, some quite interesting conversations. We'll have an OEM contact us at Polar and say, why is my board shop making up decay measurements? And the board shop says, well, we've always goal-seek the decay because we take the impedance measurement, put the cross-sections into a field solver, work the numbers out backwards, and the decay comes out at a different number. It becomes a bit glaring when they're using FR4 and it's dropped to below 2, which is less than PTFE. It doesn't often, but it's subtle bits and pieces of errors that start to creep in. So, very simple steps, and you don't have to remember these, but if somebody asks you a question about an incorrect decay on a data sheet, come back and ask me, and I can fill in the details later on. What you do is model the resistance and simulate the effect on a TDR trace. So, very simple simulation here is, I've put in the trace geometry of this differential pair, and by modelling it, the copper thickness, the copper width, we can see how much rise there's going to be in the TDR trace. And then you can remove that effect from the TDR measurement. But you can see here, if you're taking the average measurement here, if you double the length of the trace, it's going to go from a 100 ohm differential pair to a 105 ohm differential pair, 110 ohm different. Clearly, it's a nonsensical measurement, but we see this happening all the time. It's just because geometry sat at a level which were broad enough that this didn't come into effect until we're down to 75 micron lines and below, and the thinner copper substrates we're seeing now. So I've done the same model again, put thicker copper, 8mm lines, and suddenly you've got a nice flat TDR trace, so there's nothing to compensate for there. So by doing a simple graph in Excel with a tool, you can see whether the DC resistance needs to be removed from your impedance measurement or not. There are two proven methods. Some OEMs prefer one to the other. Launch point extrapolation, certainly EIPC have had many discussions about this, where basically you fit a regression line onto the TDR trace and project it back to the start of the coupon. You might say, why don't you measure a zero-length coupon? But when the coupon's very short, the interconnect from the probe interferes with the measurements. You have to wait for the bouncy interconnect from the probe to die down before you can make the measurement. So what we can do here is say, okay, I've measured a nice stable length of TDR trace, and I've projected back to the start of the coupon, and I can get the average measurement of the coupon having removed the effect of the DC series resistance. The other method, and we've had this in our tools for probably about 28 years now, and we did this for a Japanese company way back, where they just wanted to work out what the DC resistance was per inch and add that number and say, on this trace, there's 0.5 ohms per inch that needs to be removed because of the geometry, and that's called DC resistance compensation. Both work, they're both straightforward, but if you've got a PCB fabricator that's debating with a material supplier to say, I don't think your DK numbers are right, worth asking if they're compensating for DC resistance when they're using fine line traces. So there you have it. It's a case of the dance between measuring and modelling. It's not always the measurement that's right, it's not always the model that's right. You have to have a good model, and you have to have a good measurement, and you have to take into account effects that maybe you hadn't had to take into account in a previous life. And even if you don't have access to Polish tools, because I'm not being commercial here, you can simply use Ohm's law, V equals IR, and the conductivity of the ED copper to estimate this for yourself. So you can do it all free of charge. So I've given away something for nothing. Okay, so thank you very much. It's been great to speak to you again. And